Okay, today we continue our series devoted to information theory and math card magic. And we will be looking at matching color pairs. Now, this is in contrast to what we did in the last video, where the goal was to match card values. Here, we're only focused on card color. So as you can see, I have 6 red cards and 6 black cards. You can also tell that these cards are not in any particular order. Now, of course, since the two of us can see the current ordering of the cards, let's go ahead and thoroughly randomize the packet, okay? So we'll begin with something called the Charlier Shuffle, and then we'll follow that up with maybe a alternate Klondike. Okay, this is kind of a fun one. This is where you pull off the top and bottom cards off as one and go ahead and stack those into a left pile and a right pile. Now we're free to stack these however you would like. You want the left on right? Okay, that's just fine. Also, we can just do any dealing out, 2 or 3 or 4 piles. What would you like? 3 piles? Okay, so we'll do it into 3 piles. Okay, how would you like these stacked? Left to right or right to left? Okay, very good. We'll do that. Would you like me to deal out into, let's say, 2 piles? You would, okay? Would you like the cards stacked left on right or right on left? Left on right, okay? Would you like to do any more dealing into 3? Okay, 1, 2, 3. Okay, you want left to right this time? Would you like to stack into 4 piles? You would. Okay, 1, 2, 3, 4. 1, 2, 1, 2, 3, 4. Okay, why don't we do something fun? We'll stack the top piles on top of the bottom ones, or the bottom piles on top of the top ones. What would you like? Top on bottom? Okay, so we'll go ahead and just drop them on top. Would you like the left pile or the right pile on top? You want the right pile on top. Okay, very, very good. If you've seen the Pharaoh Shuffle, that's kind of a fun one. We don't have to do it, but if you'd like me to, I can. Would you like me to do a Pharaoh Shuffle? You would. Okay. Well, this is where you break the cards exactly in half, and then you perfectly interlace them. Okay. Now, it doesn't actually matter how you start the interlacing, as long as they are perfectly interlaced. That's called a Pharaoh Shuffle. Would you like to do something like a up jog? Have you heard of that before? Yeah, that's where you push forward, let's say the even position cards, and then once you've done that, you strip out the even position cards and then randomly stack these. Do you want right on left or left on right? Left on right? Okay, very, very good. Okay, and then let's do something a little different here that I'm not even sure if we've done ever in any of my videos, quite honestly. So I've just Klondike pairs to the table. So what we're going to do is build a couple of piles of 6 cards each. Now you're going to decide which cards go in each pile, okay? In fact, what we could do is designate 1 pile as yours and 1 pile as mine, if you would like. Okay, so why don't we begin with this one. Now, which of these 2 cards would you like as the bottom card in your pile? Top one? Okay, so this is the beginning. Maybe I'll turn it like this so we kind of see that that's a little different. And I'll put the remaining card at the bottom of my pile. Which pile would you like me to pick up next? Middle one? Okay. And which one would you like this time for your pile? The bottom one? Okay, and I'll get the other one. Top right? Top left. Top left there. Okay, which one would you like? Top there and bottom for me. And bottom right. Okay, we'll get my left and rights correct here. Would you like the top or the bottom? You want the top? Okay. I'll get the remaining one. This one next, okay? You want the top again? I'll get the remaining one. That's just fine. And then how about here? You want the bottom one and I get the top one. Okay, so we've created these two little piles. Now, how would you like those stacked? Right on left? Okay, very, very good. Okay, I don't know about you, but I'm feeling pretty good about these cards being beyond the knowledge of anyone. Okay, any human, any being whatsoever. Even beyond the power, even beyond the powers of AI, okay? Okay, so why don't we go ahead and deal the cards out into 6 piles. That's something we haven't done yet, so that might be kind of fun to do. So I'll go 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, so let's see where all of that mixing and scrambling and all of your random choices have led us. Okay, so let's take a look at this pair right here. Oh, that's nice. You matched 2 of them in color. Very, very, very good. Oh, wow, look at that. You got another matching color pair. Why don't we try this one down here? Oh, a couple of black cards. Whew, you are nailing it. What about over here? Oh, another pair of black cards. How are you doing this? Top one? Okay. I can't believe it. You are not going to miss any. You nailed every one of these. You created a perfect set of 6 matching color pairs. I don't know how anyone's intuition could be so amazing as to accomplish this. So congratulations. You are a superior being. Okay, well, let's talk about this. I won't talk too much about the hows and whys it works because that's not really the focus of this series. The focus of the series is to calculate the surprisal associated with what we just accomplished here. Now, how we accomplished it is something that we've talked about in many, many other places on this channel, okay? But what I could do is just quickly step through the primary elements of what we had, okay? So if you rewind the video, you'll realize that I had 2 red cards, and then I had 3 black, followed by 3 red, followed by 3 black, actually, followed by a red. Okay. Now, just in the speaking of those words, you may have noticed that I essentially said the same thing twice. Okay, there was a similarity to the sets of cards that we set out. Okay. And so what you'll notice here is we actually started with a 2-cycle structure. Now, a 2-cycle structure is where there is a repeating pattern, okay? Now, we're only focused on colors, remember. So we have red, red, black, 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 red, and then we have red, red, black, black, red. This is cyclic, okay? So this is a cyclic construction. Well, if it's cyclic, there's certain things you can do with that structure and not harm it, not change it from being what it is, namely a 2-cycle with cycle length 6. Well, one thing you can do is random cutting. You can cut anywhere. That won't hurt a cyclic packet. Something more powerful is the Charlier shuffle, which is used extensively on this channel. Okay, so all of the action here of the card movement of the cards here is equivalent to just cutting the cards at some location. Okay, so it's really just a card cut is all it is, so it doesn't hurt the intrinsic nature of this 2-cycle. From there, what I did was I did a Klondike shuffle, and if you remember a Klondike shuffle, this is where you take the top and bottom cards off as 1 and then build a pile that way. It converts 2 cycles to mirrored structures. Now, once it's mirrored, we have a whole, universe of mixing procedures that will not harm mirrored constructions. And that's primarily because of something called the stay stack principle. Okay, so with the stay stack principle, you can deal out into as many piles as you like this, as long as the number of piles is a divisor of the packet size. Well, 12 has several divisors. 2, 3, 4, and 6 divide evenly into 12. So we can deal out into 2, 3, 4, or 6 piles in the way that I've shown you here. With random stacking from left to right or right to left, we can even do what I've called a leapfrog stacking, which is something I actually used when I did the 1, 2, 3, 4, and so forth. And then I think you put the top piles on top of the bottom and so forth. None of those hurt the fact that it's mirrored at this stage. And then I Klondike the cards into just random pairs on the table. Well, they're not really random pairs, but I'm kind of scrambling the order of the pairs. And then I gave you the choice of building 2 piles of 6 cards each, one for you and one for me. Okay, and we did that by picking up any of the piles. So I picked up this pile last time as well, the one at the top. And then I gave you the choice. You could use as the bottom card of your pile either one of these. So maybe you want the top one as the beginning of your special pile, and then the other card will be the beginning of my special pile. Then maybe we'll choose this one. Which one would you like? That one there, this one here, and so forth. Now the thing you have to realize is that because it was mirrored and I Klondike shuffled pairs to the table, this is called a DMP. What's a DMP? Well, in this specific case, it means that all of the pairs are already matched up in color. Okay, these are already, now these aren't anymore because we split them, but the key is each of these pairs consists of either 2 red or 2 black. Well, it's kind of a false choice here. If I say, which one do you want? It doesn't actually matter because they're both going to be the same color, so they're both black. And then the other black card goes here. Now, you wouldn't look at them, right? We just allowed them to choose. They maybe choose a black. That one there, it was black. The other one goes here, which is also black. Okay, here's a red. And then they'll choose either one of these or both red. But if you notice at each level, as we're building these up, they're of the same color. Okay, that's essential. Okay, so now these are both black, so you'll choose just one of those black cards. The remaining black card goes on mine. Well, these are called coupled piles. Coupled piles because at each level of these piles, the cards are of the same color. Well, when you have coupled piles, you can randomly stack those 2 halves, and you have a 2 cycle with cycle length 6. So in some sense, we're like back to the beginning. Now, the cards will be scrambled quite a bit from what they were before, but that doesn't actually matter. It's still a 2 cycle. Well, being a 2 cycle to finish, think about it. If the top 6 cards form a certain pattern, you might even want to think of like 1, 2, 3, 4, 5, 6. There's some kind of pattern. And the next set of 6 cards also follow that same pattern of 1, 2, 3, 4, 5, 6. Then when we deal them out into 6 piles in this way, I've just run through all of the cards in one of the halves. And now this one will be the same as that one the same as that one, and so forth. Okay, so we'll just be building, once again, what's called a DMP, distinct mirrored pairs. But the point is, at this stage, these will actually match in color, guaranteed. Okay, so we will have perfectly matched them up in color, despite the many choices made by the spectator and the several mixing procedures that we put it through. Now, in this second sweep through this effect, I didn't do as much mixing, of course. I did in the original presentation. But the point is, we succeeded. We were able to take what seemed to be a random collection of 6 red and 6 black, and then mix, 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 and somehow separate those so that they came out in this sort of way here, where each pair consists of the same color. Well, how likely is that to happen? Okay? How likely, so think, another way to think about it is, how likely is it that if you just mix the cards, I mean, genuinely just mix the cards, okay, and then you just started making color, pairs. Okay, I'll pair these together, whoops, pair those together, maybe these two together, and so forth. I mean, what are the chances that these all match in color? Well, pretty small, right? So we've got one there, got one there, okay, blew it there. We're doing fairly well, probably because I didn't mix them very well. That's my fault. Okay, so there we go. We got 4 of them to match in color, but 2 of the pairs did not. Okay, and so you can try that out. Just mix these 6 red and 6 black, and then randomly put them in pairs, and it will take you quite a long time, by chance alone, to match them up in color. Okay, so it's pretty unusual for this to have turned out the way that it did. Well, we've been talking about ways of measuring the likelihood of certain outcomes, and in particular, the surprisal associated with certain random events. Okay, so what is the surprisal associated with succeeding in the way that I did in both of those performances? Well, to figure that out, we have to first calculate the probability of doing what we did, finishing in the way that we did. What's the chance that that would happen just randomly? Okay, so that's what we're looking at today, is calculating the surprisal for any such performance where you have an equal number of red cards and black cards. And in the end, you match them up perfectly. So here we consider a variation on matching values where there are 4 X dichotomous values. For example, 2X red cards and 2X black cards. Or more generally, 2X zeros and 2X ones. So we can let the zeros and ones denote the 2 colors, red and black. And what I thought we would do is follow the particulars of a 12-card packet to see the derivation in action. And it's not too difficult to see how from here you can generalize all of the steps involved. Okay, so why don't we go ahead and in our mind's eye, we'll just picture the packet of cards I just worked with. So maybe we have 6 black cards and 6 red cards, denoted by 0 and 1s, okay? Well, what we're wondering here is, if you think back to the original structure that I had, it was actually a 2-cycle relative to card color. And as has been mentioned in this series multiple times, the surprisal value for a 2-cycle and a corresponding mirrored representation of that 2-cycle, along with an AMP representation of the structure of that 2-cycle, all 3 of those packet structures have the same probability of occurring by chance alone, which means they have the same surprisal value. Consequently, we can decide to find the surprisal value for a 2-cycle relative to card color, or a mirrored structure relative to card color, or an AMP structure relative to card color. So here I've decided to calculate and work with 2-cycle structures, okay? So what we're looking at is how many ways can we construct 2 cycles using these numerals here, using a 0 or a 1. So the first observation is the following, that if this is going to be a 2-cycle relative to these 2 dichotomous values, the moment I put one of these 12 values in that first slot, in fact, why don't we go ahead, I'll just kind of show you a specific case of building a 2-cycle from these elements here. So let's say we happen to put a 1 right there. So we've used up one of these, okay? Well, for this to be a 2-cycle relative to these dichotomous values here, if I have a 1 here, then I have to come over here, and in the corresponding place in the second half of this packet, I need to have a 1 at the beginning of that cycle, okay? So remember, this is a 2-cycle. I've drawn a line to denote the center of the 2-cycle. And so it's a 2-cycle with cycle length 6, because each half has 6 elements in it, okay? So let's say I put a 1 here. That means a 1 has to go there. I could actually put another 1 right here. But if I do that, for it to be a 2-cycle relative to these dichotomous values here, I'd have to have a 1 here. Maybe I put a 0 over here. Well, that forces me to put one of the zeros over here, okay? And I could even have another 0 here, which would force me to have a 0 here, okay? Now, the thing I have to realize and watch out for is we're going to have 3 zeros and 3 1s on each side, right, for this to work. So I could actually have another 0 here. I still have some zeros left, forcing me to use the remaining 0 right there. And now I really don't have too much freedom. I have to put a 1 here, and the final 1 would have to go here. Okay, so this is just one of many, many 2-cycles that can be constructed using the values listed in the set here. Okay, now we do also need to remember that despite the fact that the first 6 are zeros, we are viewing these as distinguishable. Okay, so they're equivalent in value, but we're treating these as distinguishable. Well, that was the case for the cards. I had 6 black cards. Well, they were distinguishable because they had different suits and different values on them. So there were actually 6 different black cards. And I also had 6 different red cards. Okay, so as you might imagine, this is just one of many. Okay, many. Okay, so that's observation 1. Okay, so we'll have to have 3 zeros and 3 1s on each half, okay? Observation 2, the number of permissible configurations of, say, the left-hand side of a 2-cycle consisting of the above-mentioned zeros and 1s is equal to the combination calculation of 2x, choose x. Okay, so what does that mean here, okay? Going back up to the top here, notice we have 4x total values or cards. We have 2x red and 2x black. Okay, so the x that we're talking about, x is equal to 3 in our particular example here. It's because we have 2 times 3, which is 6, black cards, and 2 times 3, which is 6, red cards. Okay, so our x is 3. So in the general case, where they talk about, in fact, let's go ahead and just write it out for clarity here. So we're looking at, so n, choose r, and in the general case, it's 2x, comma x. Well, in our case, it's going to be ncr, now x is 3, so this is going to be 6, choose 3. So this represents the number of combinations of 6 objects taken 3 at a time. Okay, so that's what our specific calculation will look like for this 12-card example. So what I'm claiming here, and we can read it, I guess, in the general case first, the number of permissible configurations, okay, we'll have to define what that is, of, say, the left-hand side of the 2-cycle is equal to this calculation here. Well, here's the justification for that. Note that there are 2x positions for these values to occupy, okay, on the left-hand side of the 2-cycle. Hence, there are 2x, choose x, choices of positions on the left-hand side of the 2-cycle for the x zeros to occupy. Once these are selected, the overall configuration of the 2-cycle is determined. Okay, what in the world is that saying? Okay, so what is a configuration? Configuration is where we're just looking at the skeletal structure of the 2-cycle, okay? So if you notice here, we have 2 1s, okay, next to each other. Well, that could correspond to, like, if we have a 1 for now, representing a square, and a 0 representing a triangle, this particular configuration could be represented by what? A square, square, triangle, 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 and square. Okay. Well, we know that we have to have that same structure over here. That was the whole point, right? That's what's required for it to be a 2-cycle, right? So I'll go ahead and just repeat that. Okay, so a configuration, it's almost like a bird's eye view of the structure in which we're not at this moment worried about which particular ones are like in this position and this one. We're just focused on the fact that there is a 1. There's a 1 here, some 0 here, some other 0 here, some other 0 here, and one of the other ones here, okay? So once again, I think the best phrase is skeletal structure, in which we're going to fill out the details later, okay? Now, you can't have any kind of structure you like and have it be a 2-cycle, right? So I couldn't have this. Okay, see if you can figure out what the problem is here. Okay, and we could even go like that. Okay, do you spot any problems? Okay, what problem do we run into? There's many problems you can run into. Well, this is really not a skeletal structure for a 2-cycle, right? Okay, this needs to match that. Great. This needs to match that, which it doesn't, okay? And some of these others don't match as well, okay? So the skeletal structure is kind of giving you an overall view of where values of a certain kind can be placed so that when those values are in place, it truly is a 2-cycle relative to the values 0 and 1. So the question is, how many ways can you create these skeletal structures? I call them configurations. Well, the way to look at it is to consider the positions of things. So, for example, maybe I'll do it in red. So this is in position, this is position 1, 2, 3, 4, 5, 6. Okay? So we're only going to focus on the left-hand side. Now, why is that? Well, it's for the reason that we just showed in that example. Once you lay out a permissible configuration on the left, the second half of the cycle needs to be an exact copy of that skeletal structure, okay? So if I have 2 squares here, I have to begin with 2 squares here, and then a triangle, and so forth, okay? So really, you can focus on just either half, because once that's laid down, the other half has to be a copy of that skeletal structure, okay? Well, how many ways can you have these 3 squares and these 3 triangles arranged on the left-hand side? And so we're wondering, how many different ways can you choose 3 of the 6 positions that these objects can be in? Because the number of ways of choosing 3 positions among the 6 positions will actually give us the number of skeletal structures that can be formed using these squares and triangles, okay? So the number of configurations of the left-hand side is NCR, so 6, choose 3. And so what are we choosing? What's the larger set of 6 objects? It's the 6 positions. 1, 2, 3, 4, 5, 6. What's the 3? It's the 3 positions that you're going to select to, let's say, put the squares there or put the triangles there. Okay? So what are all the different ways that you can select the 6 positions 3 at a time. Okay, that's really all we're calculating. So it truly is NCR, so 6, choose 3. And as we mentioned before, once the left-hand side is determined, the right-hand side is forced to be an exact copy. So you won't be counting any more overall 2 cycles, okay? So the number of left-hand structures that you can create will be the same as the total number of 2 cycles you can create with that skeletal structure, okay? That's what I'm explaining down here. So the 6 here refers to the number of positions to choose from on the left-hand side of the 2 cycle, and the 3 refers to the number of positions chosen for, let's say, the zeros or for the ones, or as graphically depicted for the squares or the triangles. Okay, so we have our first calculation here, the total number of skeletal structures, which I've called configurations, for a 2 cycle consisting of dichotomous values, like we've listed here, will be 6, choose 3. Okay, very good. Okay, so that's observation 2. Now, observation 3 is a bit more subtle, so let's take a look at that. Each of the configurations, each of the skeletal structures we've kind of counted, which is the 6, choose 3, identified in observation 2, yields this number of unique 2 cycles. Wow. So it's x factorial raised to the 4th. Wow, how did we get that? Well, we'll show you. Times, and then we have NCR 2x, choose x, times NCR 2x, choose x. So how do we count this? Well, here's the conclusion. This is the conclusion using the values that we're working with relative to this 12-card packet. Remember, x is 3 for us right now. Okay, so we have x factorial, 3 factorial to the 4th, and then this I've just placed x in for 3 in for x, so this is 2x, and then that's x. Okay, so let's take a look at how we got these different factors in our total count of the number of 2 cycles that can be formed for each configuration. That's important. So once we get this answer here, if this answer is correct for this statement, then it will be important that we take this product here and multiply it by the number of distinct configurations, which we've already found. It's this right here, okay? And in fact, if you keep that in mind, you'll recognize that later. In fact, why don't we go ahead and just, if you don't mind, we'll take a little peek here at the general formula. So in the general formula, you'll notice that there's an NCR 2x, choose x, to the 3rd power, okay? So we're now explaining kind of where all of that comes from. Now, in observation 3, we only get it to the 2nd power, but this will be multiplied by this quantity, boosting it to the 3rd power, okay? Well, how did we get this product? Well, the idea is to imagine considering any one specific skeletal structure. Okay, so why don't we go ahead and just work with the one that I've drawn on the previous page for observation 2. Okay, so to understand where this 3 factorial to the 4th comes, recall that we already have established that to be able to create a 2 cycle relative to these values 0 and 1, we're going to have 3 zeros over here and 3 ones. So if for now, if you want to picture the squares as the zeros, so what that would mean then is in this position marked with a square, any one of the 3 distinct zeros can go there, right? So once again, remember, even though these look the same, they are distinguishable. Even though these are 6 black cards, they are physically different cards, okay? And that's actually was the case with the performance, right? So we would have any one of those 3 zeros or black cards could go here. Now, once we have that in place, The one next to it needs to be of the same color, but we only have 2 of the 3 left. So I have a 2 here, okay? Well, and then for the first triangle, this can be any one of the, I guess we're going to have, remember the squares are zeros. This is like having a 0, a 0, and then the triangle will be a 1. It can be any one of the 3 ones designated for this half, okay? Now, when we get down here to our third square, that's our third 0, there's only one choice, right? Because we've used up 2 of the 3. So the final 0 has to go there. How many choices would we have for this position here, marked by a triangle? Well, we've only used 1 of the 3 ones, so we still have 2 of them left. And then once that one's down, we only have 1 left. Okay, there's only one choice for what will fill that spot. Okay, now everything I said here applies over here as well. You have 3 zeros and 3 ones that are going to be put into these special positions. And so if we, for it to be a 2 cycle, this has got to be a 0, right? I mean, you have to have the same value at the beginning of each of the 2 cycles for it to be a 2 cycle. Okay, so any one of the 3 zeros can go there. Any one of the remaining 2 zeros can go there. Any one of the 3 ones can go there. You don't have a choice here. There's only 1 0 left of the 3. You've used 2. You have 1 left. You have 2 ones left. So there's the 2 down there. And then you only have 1 left. Okay, so what we're doing here now is we're just using the fundamental counting principle. It's also called the multiplication principle. Okay, so this is just going to calculate for us the total number of ways of doing this, total number of ways of putting zeros and ones in these special places. Well, if you look at it, we get it like right here. We get a 3 times a 2, and then if you want to pair it up with the 1 here, that would be fine. So that's like 3 times 2 times 1. Well, that's 3 factorial. Come over here. Right here, this is, I don't know if I should use, maybe I'll underline it or something, but right here we have a 3, and then we have a 2, and then we have a 1, of course, which is not going to make a difference to the product, but that's another 3 factorial, so another factor of 3 factorial. And then the same thing here, right? So we have 3 times 2 times the 1 is a third 3 factorial. And then we have our fourth 3 factorial right there. Okay, so the total number of ways of putting these sets of 3 zeros and 3 ones into these various locations is 3 factorial to the 4th. Now in the general case, it's x factorial to the 4th, right? So that's what we're seeing down here. Okay, so we've kind of explained this part here. Now, where did this come from? Why do we have that for helping us count the total number of 2 cycles that can be formed having a specific, that's key, a specific configuration? Oh, and I apologize. It looks like the second computation I wrote up, we've done first in the video just now. So I kind of have those. It doesn't actually matter. So we found this first, and now we're going to figure out that. Well, this is explained first on my write-up, so apologize if that's confusing. Okay, so we're going to work on this, figure out what that is. Okay, so to get this, in fact, think about it. We have a total of 6 zeros to choose from and 6 ones. Well, we're needing to choose 3 of these zeros to go on the left-hand side of the 2 cycle, and 3 of these ones to go on the left-hand side of the 2 cycle. And then all of the remaining zeros and ones will be designated to fill the spots on the right-hand side. Okay? So we have 6 zeros, and we're going to choose 3 at a time. How many ways can you do that? Well, that's just 6 choose 3. Okay, same thing for the ones. How many ways can you choose 3 ones at a time from a set of 6 of them? Well, it's just 6 choose 3 for the ones as well. Okay, so we get the same factor twice. which leads to this term right here. So we've just squared it. And then we've already explained the bottom here. We explained that first. Okay, so what we've done then is for each specific configuration, we've calculated how many 2 cycles can be built that have that skeletal structure. Okay, now to get the total number of 2 cycles, all we need to do now is just multiply our answer here by our previous answer here, right? Remember, this is the total number of configurations or skeletal structures. And then this is the total number of 2 cycles for each of those configurations. So if you multiply all of that, you'll get the total number of 2 cycles that can be formed using 6 zeros and 6 ones. So this will be the total number that can actually be constructed. And so if you go down here to our probability and surprisal calculations, okay, so for the probability calculation, the top is the total number of 2 cycles using the zeros and ones as specified above. Then we have to divide it by the total number of orderings of all of those 12 objects or 12 elements. So how many ways, if these are being viewed as distinguishable, so there's 12 distinct objects. Well, how many ways can you order 12 distinct objects? Well, it's 12 factorial. Or in this general case, it's 4x factorial, okay? So this fraction here truly gives you the probability that by chance alone and just mixing the cards that we would actually get a 2-cycle structure, okay? And in our particular case, I've just put in the individual values. Once again, x is 3, and here it's 4x, so that's 12, and so forth. And we can even look this up on the chart. So if we go down here to the table, so we're looking at x is 3. Here's x is 3. So here's the probability. There's about a 2% chance that you would take those 12 cards, mix them, and then find that that set of 12 is a 2-cycle relative to card color. Okay, about a 2% chance. Okay, well, it could happen, but it's not very likely. And then from there, once you have the probability of a random event, the surprisal is a fairly easy thing to find. It's always log base 2 of 1 over the probability of that event occurring. And so 1 over the probability just reciprocates the fraction, just flips it. So the second expression truly gives you the surprisal value. So for the particular performance that we did at the beginning, the surprisal value, here we're looking at x is 3, is actually going to be 5.53, I guess, bits. Okay. Now, do you remember some of the interpretations that we gave for that? So let's say 5.5, technically it would round up here to 6, but if we want to be conservative, I guess we can round it down. So we'll say 5 bits of surprisal. Well, what does that mean? 5 bits of surprisal is the degree of surprise one would experience in watching someone else toss 5 fair coins high up into the air, and while in the air, that person says they're all going to land heads up. And they do. Each of the 5 coins, once it settles down on the table, is heads up. And that person predicted it correctly ahead of time. So that is the level of surprise associated with the performance I showed you. Well, 5 bits of surprisal is quite surprising, but it's not going to take your breath away, right? And that was probably true for the performance. You thought, oh, yeah, that's kind of cool. But it's not like hairs on the back of your neck went up or something, because it was almost freaky that something so unusual could happen, right? But it's still quite respectable. 5 bits of surprisal. Now, of course, if you're wanting to ramp up the surprisal level, you just use a larger packet of cards. So if we were to double the number of cards from 12 to 24, where you have 12 red and 12 black, and then mix, 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 and then in the end pair them up by color, then the surprisal jumps quite a bit. So there, x would be 6, right? Because the total packet size is 4x, so 4 times 6 is 24 cards. Well, the Surprisal value now is, it's over 11 bits. Okay, that's getting pretty darn surprising. 11 bits. Okay, so the other example that we gave, or interpretation, you can interpret this in terms of answering correctly on a true-false test or quiz. So here, 11 bits of Surprisal would be the level of surprise one would experience in randomly guessing on an 11-question true-false quiz, just totally guessing, true, false, false, true, and in the end, score 100% on the quiz. And you really just closed your eyes or had no idea what the answers were. Well, that person doing that would be incredibly excited seeing that happen, right? Because it would be very unlikely to happen by chance alone, okay? So that is, another of many interpretations you can give to these bits of Surprisal, okay? I should also point out that I have a graph here of the probability calculations, of course, down here. They go towards 0 very quickly, and we can see that in the table. And then the Surprisal values climb quite quickly. So thank you again for watching, and I encourage you to take a look at the next video in this series.